Hi Year 13. In this video, I'm going to show you how to form a differential equation and then go on to solve it, as we've seen in a previous lesson. This is the end of the integration chapter, so we're going to tie together everything we've learnt so far and put it into a modelling context, as is kind of usual with these A-level chapters. So we're starting off with a famous example of a differential equation that occurs out of nature, and that's to do with the rate of growth of a population. So let's highlight the key information in this paragraph, and we'll kind of talk about what it means and how we're going to write down that information as a differential equation. So we've got the rate of increase of a population, and rate here is a key word that we've seen before and is indicating that you need some kind of derivative with respect to time. The population we're calling P and time is T, and we're saying that the rate of increase is proportional to the current population. So proportional to is going to be quite common with these questions. A lot of proportionality statements will appear, and this is going to involve setting up an equation that has some kind of proportionality constant in. So I'll remind you of how that's going to work. So we've got direct proportion. Let's just stick with the variables y and x for now. So if y is directly proportional to x, then the notation is as follows. We've got y proportional symbol and x, and then as an equation we've got y equals k times x, where k is a constant. Okay, so our aim is to set up an equation that links the two variables together, but one of these things is going to be a derivative, as we've seen here. Okay, that's direct proportion. We've also got inverse proportion as well. So if y is inversely proportional to x, that means that we write it this way, y proportional and then 1 over x. And then as an equation, you've got y equals k over x like this. And again, k is a constant. Right, so look out for these words. You've got to use those in order to set up the appropriate equation there. Let's have a go at doing this with what we've got up here in this paragraph then. So we've got the rate of increase. That's going to be the population rate of growth, which is dp by dt. We're saying it's proportional to, and by default, we're calling this direct proportion, unless it says otherwise. And it's proportional to the current population, which is p. Okay, so that's adjusting this, but using our derivative and p. The equation form of this then is going to be dp by dt equals k times p, where k is a constant. Right, that's our general differential equation solved. We're now going to solve it and think about and discover what kind of function fits this property. You've probably already thought of it because you know it's to do with population growth, but we'll see. So hopefully you've got this part down. I'm going to get rid of this. Okay, so let's solve this equation. I'll start by writing it out again. Now, this kind of equation is in separable form because what I can do is I can isolate the p terms on the left side with the dp and the rest of the terms on the right side with dt. Now, I don't want to bring too much back to the dp side because I'm trying to eventually solve for p. So it helps to bring as little as possible back to the dp side. So 1 over p is what this comes across. I'm going to leave the k where it is. And then on the right side, I've got k dt. Great. That's the variable separated. I'm now going to integrate both sides. And that will give me natural log of the absolute value of p. And then k is a constant, remember, and if we integrate that with respect to t, we're going to get kt plus our constant of integration. Right, to then solve for p, we're going to exponentiate base e, and that's going to give me absolute value of p equals e to the kt plus c. Okay, and then if you remember before, rather than have our constant of integration as a power, we break off a separate base e and then put it at the front as a separate constant. So now I'm going to change to this. I'm going to do p equals a e to the kt. and A is some constant, and so is K. Okay. The reason why I can take off the absolute values is because this can be plus or minus, so it takes care of these absolute value bars. So you don't particularly need to worry about those. Right, that is the general form of our differential of our general solution, which, as you probably expected, is exponential and solves this property here. Okay, the derivative of an exponential is proportional to itself. Okay, great. So if you're unlucky enough to not have the differential equation, you may have to solve it, but it'll probably be something simple like this with a proportionality statement in there somewhere. Right, let's look at a couple more examples, shall we? Okay, so this is a quite common setup for an exam style question. You've got some kind of container normally that's filling up with water or some liquid and might be leaking out water at the bottom as well. So here's the picture of what we've got, a large cylindrical tank. The diameter is 20 meters and the height of the water is h. Water's flowing out of the bottom of the tank through a tap at a rate proportional to the cube root of the volume. So lots of keywords there that allows us to write some things down. So I'm going to highlight rate, which is going to give me the rate of water flow, which is going to be dV by dt. And this time we're proportional to the cube root of the volume. Again, by default, we're talking about direct proportion, and this time our volume is being cube rooted as well. Also, the water's flowing out. That's also important. So if the water's flowing out, then this rate of water is going to be negative because of the decrease in the water as it comes out. So I'm going to set up a differential equation using this information. To start with, I'm going to look at the geometry of the problem. I've got a cylinder, which I can work out the volume for, because that's going to be involved in the problem. So let's do that first. So the volume of the water is, well, it's a cylinder, which is going to be pi r squared h. R is going to be 10 meters because it's half of the diameter. So that's going to be this, pi times 10 squared times h, but that's 100 pi h. Great. Now what I can do with this, with my volume given in terms of h, I can now get one of my derivatives that I will need, which is going to be dV by dH. And if I differentiate this with respect to h, I'm just going to get 100 pi because that's the constant in front. Now I can use the proportionality statement in the question. I can write down another derivative, that's dV by dt. Okay, it's proportional to the cube root of the volume. Now I'm going to go straight to the equation form of this. But what I'm also going to notice is that because the water's flowing out, I'm going to need a minus sign to show that this is decreasing the volume. Minus k times the cube root of the volume. Okay, so because we're not quite done yet, we're going to need to do some rearranging and combining of constants. It's not very good to call this constant here k because it's supposed to be k at the end of the question. So to differentiate it, I'm going to call it k dash, just to make it different from the k that we're supposed to get at the end. Now I can replace v with my expression for v, which is 100 pi h. And that gets us closer to having it look like the answer at the top. And then to change from dV by dt to the derivative I want, which is dH by dt, I'm going to use the chain rule. So let's set up some chain rule. We've got dH by dt. dH goes on the top left, dt on the bottom right, and then the other two bits are going to cancel out, and that's clearly going to be dV. Now both of these I've worked out, except this one, I need to take the reciprocal to get dH by dV. So this will be 1 over 100 pi times dV by dt is minus k dash times the cube root of 100 pi h. Excellent. Now I'm going to continue. I'm going to combine some constants together and write it eventually in the form that I want. So dH by dt is, let's put the constant at the front, it's minus k dash over 100 pi. Now I'm going to split the cube root into two separate cube roots in order to isolate cube root of h on its own. So this will be cube root of 100 pi times the cube root of h, like that. And now what you notice is that everything except this final term is just a constant, even though k dash is an arbitrary constant. So all of this stuff now, I'm going to relabel as just being some new arbitrary constant, which I'm going to call k. And then we're done. So I'm going to finally write out what we're supposed to have. dh by dt equals minus k cube root of h, as required. Right, A's done. Now we're going to solve this equation and show that the general solution of this differential equation is written in this form. So h is p minus qt to the power of 3/2. P and q are constants as well. And then we're going to sort out what happens with the end. So if I clear the page, I can then move on to solve part B. So to solve B, let's mark it up as that. We're going to solve this equation. Let me write it again. This is again in separable form. I need to get the h's to this side, so I'm going to divide by the cube root of h, but that's going to turn it into this. It'll be 1 over the cube root of h will be h to the minus a third. dh equals minus k dt. Okay, put in some intermediate steps if you're not sure how I got to that. We're now going to integrate both sides. Integrating this left side will make us have h to the 2/3, and then divided by that 2/3 is going to give you 3/2. On the right side, integrating this minus k, which is a constant with respect to t, gives you minus kt, and then we're going to add c. Okay. Now I've not used p and q yet, but hopefully when I've got it in the desired form, I can do some relabeling of constants at the end. So now let's solve for h. I need to firstly clear this 3/2 fraction. So h to the 2/3 is 2/3 because I can flip this to the other side. Maybe let's expand the bracket so we can then raise to a power next. So this is minus 2/3 kt plus 2/3 of c. And then to clear the power, I'm going to cube everything and then square root, which is the same as raising to the 3/2. Excellent. Right, now we're done because we've got the desired form and we can relabel these constants around our variables as p and q accordingly. So notice I need to swap the order of these terms so that the t term comes second. And then 2/3 c, we're going to relabel as p. And then minus 2/3 k is another constant. We're going to label that as minus q, because we need that minus sign there. So we're done because we can write this. This is p minus qt to the power of 3/2. Okay, now we're in a position to solve C. So initially, the height of the water is 27 meters. Now, initially is kind of a key word to have kind of stored in your brain because initially is what happens when t equals 0. So that gives you information about what's going on with this equation here. Initially, the height of the water is 27, and then 10 minutes later, the height is 8. So 10 minutes later, obviously, it will be when t equals 10. Make sure that t is in fact in minutes. I think somewhere it's going to say that. Yes, t minutes here means you've got 10 minutes. So we can use this information to sub into our solution down here to figure out p and q. So let's do the initial one first. So t is 0. H is, okay, using this form, p minus 0, 0t there, to the power of 3/2. But the height of the water is 27. So we can write it as 27 like that. Then solving for p, I'm going to cube root both sides first. that takes off the 3 in the power. That's going to make 3, and then I'm going to square both sides, so p is 9. Okay, so cube root and then square. Great, so p is 9. I can then use the fact that when t is 10, h is 8, and do the same thing. So 8 is the height. That's, I know p what p is now, it's 9. 9 minus qt. Oh, sorry, t is 10, isn't it? So 9 minus 10q. You're welcome. Gives it that. I can now, sorry, I did it again, 10q. 10q, there we go, to the 3/2. Okay, good. Right, now I can solve this. So I'm going to cube root. And then that's to the power of half. I can then square to clear the half. And then solve this for q. So this is going to give me 10q equals 5, 9 minus 4, and then q equals a half. Okay, so those are solved. What you probably now want to do is rewrite your equation, an expression for h using these constants. So now we've got this, we've got h equals 9 minus a half of t to the power of 3/2. Now the time in minutes when the water is at a depth of 1, I'm going to do that under here. So when the depth is 1, that's my value of h. So 1 equals 9 minus a half. I don't know the value of time yet, so I can solve for that now. So then I can easily get rid of this power because it's acting on 1. I can square it in cube root and it's going to stay as 1. And then solve for t. So 9 minus 1 is 8 equals half of t. Double and I get t is 16. And that's in minutes. Okay, so that's a fairly comprehensive example there, and hopefully you followed along with the steps. Maybe let's see one more example just to kind of get the hang of it, and then I'll leave it to you to maybe do some yourself. I may also make a video going through some of the examples on the exercise to give you a hand as well. Okay, final example. This is another liquid in a container example, so quite a good one to be able to practice and do. So liquid is pouring into a container at a constant rate of 20 centimeters cubed per second. Again, we've got this word rate we've got to pay attention to, and it's leaking out at a rate proportional to the volume of the liquid already in the container. So this looks similar to the rabbits that we had before. We've got proportional to the current value. We've also got this rate here. Now, this is combining rates in and out. So what you have to do there is do a difference between the rates. So I'm going to set this up as a little word equation. So if you've got rates in and out, then that's going to be the rate in minus the rate out. Okay, it's quite common for these kind of questions. So this rate over here is kind of like the net rate. It's like the overall rate as to what's happening to this container. And you have to do rate in minus rate out. Okay, the rate in is this constant rate of 20. So let's write that down. So the rate in equals 20. Okay, just a constant number for the rate. And it's leaking out proportional to the current volume. So that's going to be K times V. Okay, so this basically sets up how our equation is going to work. Our rate is in minus out. The rate overall is the change in volume over time. The rate in is 20, and the rate out is KV. Okay, so some sentences to explain these things are probably going to help you out. I've written down what I would write down, but let's see what the box says to make sure we've got all the right wording. So dV by dt is the rate of increase of volume with respect to time. So define dV by dt. Minus kV. K is a constant of proportionality, and the negative shows decrease. The signs of things are important here. If it's increasing, then have it as positive. If it's negative, have it as minus your constant. and then putting it all together makes this. That's 2 marks. For part B, we're now going to solve the equation, and we're also given this bit that's easy to miss, which is that the container is initially empty. Let's write down what that means. That means that when t is 0, the volume is 0, because it's empty. Now we're going to solve the equation. So write it out again. Now, this doesn't quite look like it, but this is in fact separable. We've got one single term here as a factor that contains the variable v. I need to get all of that to the other side this time because this doesn't break apart as 2 separate factors, it's a sum. So I've got to get it all across to put it like this. It's 1 over 20 minus kv dv equals, and then everything's gone from this side, so it's just 1 dt if you like. Okay, again, I can't add kv to this side because how separable form works is that it's got to be a product here, and that's not a product, so it's got to all come over. Integrate both sides. So this is going to give me some kind of natural log because it's of the form 1 over v. I'm expecting a minus k at the top to match the derivative over here. So this, I believe, is going to go to minus 1 over k times the natural log of 20 minus kv. Okay, if you want to check that, if you differentiate this, the natural log will give you 1 over 20 minus kv, but then it will also give you minus k on the top, and the minus 1 over k there is going to cancel that minus k out. On the right side, you're going to get just t plus c. And now our aim is to solve for v now. So I've got to try and rearrange in such a way to get to v. So the first thing I'm going to do is times by minus k. So now ln of 20 minus kv equals minus kt minus kc. I can now exponentiate. So 20 minus kv equals e to the minus kt minus kc. Now, this is getting quite an awkward thing to be able to manipulate. So I think a good thing to do now is to use my initial conditions to figure out some of these constants. So I'm going to actually go back a step to here and put my boundary conditions in and see what I get. So let's start this so we can connect them. So then natural log of 20 minus 0 equals, and then t is 0 as well, so that's minus kc. Okay, right, I think maybe it's a good idea to write this out again then with our constants in. So now we've got this, we've got natural log of 20 minus kv equals minus kt, and then minus kc is natural log of 20. Okay, right, I think best thing to do now is to combine the natural logs on one side. So I'm going to subtract the natural log of 20. And by subtracting the logs, I can then divide the arguments. Okay, now I can exponentiate and clear the natural log. So I'm going to do that over here. So 20 minus kv over 20 equals e to the minus kt. And then we can now solve for v. So times by 20. And then rearrange terms, you've got kv equals 20 minus 20 e to the minus kt, and then I'm going to divide by k. Great. Okay, so we're done now. We've got our form for v written in the form that we want, with our a and our b being given in terms of k. Excellent. Now, given also that the dv by dt equals 10 when t equals 5, we can now actually figure out this constant k as well. We've got more information that we can sub in, and that's going to help us figure out k. But to do that, I'm going to need to take my expression for v and differentiate it, because that's going to help me get an expression for dv by dt in terms of just t. So I'm going to do that now. So I'm first going to get rid of everything on the page. Rewrite what I've now got. I've got v equals 20 over k minus 20 over k e to the minus kt. I believe that's what it was. I'm going to double check. Yes. Okay. Now we're going to use this information here. So dv by dt, we're differentiating this with respect to t. This is a constant, which is going to disappear. It's this part that needs differentiating, and what's going to happen is you're going to get the same power of e again, because it's an exponential, but then the minus k in front of t is going to drop down to the front, giving you positive 20 e to the minus kt. Okay, that's using the chain rule with that inner function up there. It's equal to 10 when t is 5. So 10 equals 20 e to the minus 5k. That's replacing t with 5 and dv by dt with 10. Now we can solve for k. So I'm going to divide by 20. That gives me 10 over 20 is a half, e to the minus 5k. I'm now going to take natural logs. Natural log of half equals minus 5k. Now what I'm going to do is I'm going to multiply by minus 1, but multiplying this log by minus 1 at the front is going to flip this half back to a 2. So I can now do this. Natural log of 2 equals 5k, and then I'm going to divide by 5. Equals k. Okay, that's important. That means I can now go back to my expression for v and write it without the values of k. And then we're going to find the volume of liquid in the container at up to 10 seconds. So this means v equals 20 over k. That's my value of k, minus 20 over a fifth ln of 2 times e to the minus kt. So that's minus a fifth ln 2 times t. Okay, let's tidy up. So if I times top and bottom by 5, I'm going to get 100 over the natural log of 2. Same for this part, times by 5 on the top, times by 5 on the bottom. And then this part, I can deal with this e in the natural log by doing something here. So what have we got? So this is going to be e to the natural log of 2 to the power of minus a fifth. And then that's going to be raised to the power of t so that these two things can times together. And then my e and natural log can cancel out. Right, last thing to write down then. So v equals 100 over natural log of 2 minus 100 over natural log of 2 times 2 to the minus a fifth to the power of t. And that's my expression for v. Now, when t is 10, I can plug that into my calculator and work out the value of v. T equals 10, v equals. Okay, I'm doing this as carefully as I can. Times by 100 over natural log of 2. Times minus 1 plus 100 over natural log of 2. Okay, I make 108.2. And what units have we got? We've got volume is given in centimeters cubed, so that's going to be that. Okay, I'm just going to check that, make sure we've got everything right, and then if I'm lucky, then we can call it a day for this video, and then I might make some more examples in a separate video. Okay, good. I'll switch rounds to 108. The exact value, if you were to do that, is going to be this, 75 over natural log of 2. Okay, quite a lot of steps there. Hopefully you followed along. There's a lot of difficult tidying up in this. You've got to be really confident with log rules. and also subbing things in and solving exponential equations too. So best of luck with these. I'm going to make some more videos, hopefully with some more examples, and I'll leave you to get on with some yourself. All right, thanks, year 13. See you soon.